So, hello and welcome to this lesson in our study of optimization 2. So, this happens to be the sixth lesson, and note that so far you've been learning how to solve linear programming models, right? We learned the graphical method, which is applicable when we have just two decision variables. But I know in real life problems, we mostly deal with more than two decision variables, so we introduce the simplest algorithm, right? And based on the simplest algorithm, we can have um some methods like the two-phase method, the big M method, and what have you. Okay, so in this lesson, which happens to be the sixth lesson, we would want to talk about duality and sensitivity analysis. Okay, so before we get into it, let's try to know why we are doing this and what they imply. Okay, so duality and sensitivity analysis. Sensitivity analysis is also known as post optimality test. Okay, so in this sixth lesson, we will talk much about duality. Then in the next lesson, which is lesson 7, we will dedicate that to the sensitivity analysis. Okay, and we also try to find out the relationship between the primal problem and the dual problem. And also, if you have the final simplex tableau for a dual problem and a primal problem, how will you get the solution for the dual? So finding an optimal solution to a problem is not the only objective, but the decision maker is interested in obtaining relevant information regarding the impact of technological innovations, economies of resource utilization, and the sensitivity of the optimum solution to the changes in the model parameters. So such pertinent issues are handled by duality and sensitivity analysis or post-optimality test. Okay, so for instance, we have this model here which says we should maximize this objective function, okay, and it is a profit function. So we are trying to maximize profits. So we are maximizing z equals 6x1 plus 3x2, and it is subject to these constraints. And mostly for the constraints, the right hand side are resources. Okay, and with the objective function, the coefficients of the decision variables are profits. So let's say we have solved this model, right? And we had a certain value for x1, we had a certain value for x2, and we had a certain value for z, which is the maximum profit. But now there are changes, okay? And when you sell a product of x1, instead of getting maybe $6, now you're getting $7 here. Instead of getting $3, let's say you're getting $3.5 here. So we would want to know if the solution we found using this model, right, will still be optimal when we have 7 here instead of the 6 here, and we also have 3.5 here instead of the 3 here. So it is such issue that we mostly address using the duality and the sensitivity analysis. Mostly the sensitivity analysis, right? So we realize that when we do that in our next video, it will give us a range where we can vary these parameters and we'll still get an optimum solution. Okay, so let's learn how to formulate the dual problem. Okay, so every primal problem has its corresponding dual problem. So someone will say, what is a primal problem? When you have an LP model, the original LP model is the primal problem. So for instance, this LP model we have here is the primal problem. Alright, and every primal problem has a dual problem. And mostly when you have a primal problem, we would want to formulate a dual problem from it to get to know what we call shadow prices, okay, or marginal prices. And that helps a lot when we are trying to make decisions. So Every primal problem has its corresponding dual problem. So now how do we formulate a dual problem from a primal problem? So to do that, these characteristics here is going to help us. Okay, so let's take note of them. So the first one says that if the primal problem is a maximization problem, then the dual problem is a minimization problem and vice versa. So please take note of this. The second one says that the profit constant Cj in the primal problem replace the capacity constant Bj and vice versa. So what it implies is that, for instance, if we are writing the dual problem of this primal, you see the 6 here and the 3 here are what? The coefficients of the decision variables in the objective function. They rather become the right hand side. And the right hand side here, 15 and 40, rather become coefficients in the objective function. Okay, so that's what the second point implies. And the third one says that if the primal problem involves less than or equal to, the dual problem involves greater than or equal to, and vice versa. Then the fourth one says that in the constraint inequalities, the coefficients which were formed by going from left to right are positioned in a dual from top to the bottom and vice versa. Okay. With the rest of these characteristics, when we start formulating the dual problem from the primal problem, you get to know them. Okay. Then the fifth one says that a set of new variables appear in the dual problem. The sixth one says neglecting a number of non-negativity conditions. If there are n variables and m inequalities in the primal problem, then the dual problem will have, so it ends, it will now have m variables and n inequalities. Okay, don't worry, we will illustrate them with examples very soon, you understand. And the seventh one says the dual of the dual is the primal problem. Okay, so with everything that we've said, this is what it implies. If you have a primal problem and you want to convert it to a dual problem, you would have to write the primal problem in a form of a matrix. So let's say a matrix A, starting with the constraint, and the last entry is going to be the coefficient of the objective function. So after writing it, then you find its transpose. So E transpose becomes, so this is the primal. E transpose is what? The dual. And you see, when you find the transpose of the dual, you're going to get back towards the primal. So that's the reason why this point 7 says that the dual of the dual problem is the primal problem. I hope you get it. Alright, so I've talked much. Now let's illustrate it with examples. Okay, so consider the primal problem below. We have minimize f equals 28x1 plus 40x2 plus 20x3, and it is subject to these constraints. Okay, so as you can see here. Okay, so what we need to do is that to convert this to a dual problem, you have to write this in a matrix form. That's the simplest way of doing it. Okay, so you can see that when it comes here, we start with the constraint, right? So the first one, x1, so we can call this x1, x2, x3 in the right hand side. So you can see that the coefficient here, you have 1, 0 0.9, 0 0.8, 30, 0 0.6, 2, 0 0.7, the right hand side is 23. Then we come to the objective function, 28, 40, 20. So that's what you can see here. You know, the objective function does not have a right hand side. That's why this place is empty. So we are calling this matrix F. You know, to get a dual problem, we have to find the transpose of F. So when you find F transpose, I hope you know how to find the transpose of a matrix. Yes. So now we'll get 1, 0 0.6, 28, 0 0.92, 14. So we get what you can see here. So when we get this, you know, the fifth point said that a new set of variables appear in the dual problem. So in the primary problem, we're having x1, x2, and the rest. And so in the dual problem, we will want to have like y1, y2, and the rest. Okay, and so we'll call here y1, we'll call here y2, and this will be our right hand side, right? And these will be constrained. And the last one is always the objective function. So now from here we can write what? And if you could recall, the question was minimize. And the first point says that if the primal problem is a maximization, then the dual is a minimization problem and vice versa. So because the primal was what? Minimized, that means the dual is going to be what? A maximization. So we will say maximize f equals, but now these are what? Our these are objective functions. So 30y1 plus 23y2 subject to these constraints. So you can see y1 plus 0.6y2 less than or equal to 28, and whatever we have here. And these are non-negativity constraints. Okay, so I see, do you get it? So this here is dual, the dual form. And you can see that with the dual form, we have three inequalities. And we have two variables, decision variables. Let's go back to the primal problem. We have three decision variables, and we had what? Two inequalities. So you can see that it has changed. So three variables, two inequalities, but now we have what? Three inequalities, two variables, and that was what the seed point was trying to say, right? And the rest. And so converting a primal problem to a dual problem is very simple, okay? And y1 and y2, which if we solve this LP model, we seek to find, they are what we call shadow prices. So we will later on in the video define what they are: shadow prices or marginal prices. Okay, all right. So now let's take a second example. So this is the primal. Maximize z equals 45x1 plus 80x2 subject to this constraint, and we have to write it in dual. Can you do that? So maybe you can pause the video and try it out. So in 5, 4, 3, 2, 1. Okay, so this is going to be the dual of the primal that we had. Okay, and if you don't understand how we got it, first of all, we write this in a matrix form, starting with the inequalities first. So we get 5, 20, 400, then 10, 15, 450, then we have 45, 80, right? And when you find Z transpose, we are going to get 5, 20, 400, 10, 15, 450, and 45, 80, right? And this is y1, y2, our right hand side. And we convert it to what? This dual. So converting from primal to dual is very simple, right? So let's consider a special case. Okay, so sometimes there can be a case when some of the inequalities have equality. So you could see with the two examples that we've treated, we have less than or equal to and greater than or equal to. Oh, and I left one thing out, I think. So you could see that here with the original problem, the inequalities were greater than or equal to. When you're writing the dual problem, we did it what? Less than or equal to, right? Because of this point here, the third one, if the primal problem involves less than or equal to, the dual problem involves greater than or equal to, and vice versa. Okay, so I hope you get that. Okay, so you see special case, that's when any of our constraints have an equality. So let's see how we do that. So you can see that here the primal problem is maximize this subject to these constraints, and with the third constraint we have an equality. So before we can convert this to the dual form, okay, this equality, we will have to change it to inequality. And changing equality to inequality is will give us two constraints. One will have less than or equal to, and the other will have greater than or equal to. So we are going to have this. So you see, we are having 3x1 plus 4x2 equals 50. But now we have to change it to inequality. So it will give us two constraints. One will be less than or equal to, one will be greater than or equal to, which will be what you can see here. Hope you can see that. Alright. Then for uniformity, we would want to convert this all towards less than or equal to. Okay. So to do that, that means you have to multiply this through by -1, and also multiply this through by what? -1. So doing that, we are going to get what you can see here. Right? Okay. Then we would have to now write this in the matrix form. Right? So writing this in the matrix form gives us this. We find the transpose, and that gives us this. Right? And we use new variables for it. So y1, y2, y3, y4, and this is our right hand side. Then we can then the original problem was what? A maximization problem. So the primal will be a minimization problem, and with your original problem, that's the primal problem, our inequalities were less than or equal to. So with the dual, it will be greater than or equal to. Okay. So this is how we convert a primal problem to a dual problem, which is very simple. Okay. Now let's talk about what we call the duality theorem. So it says that if either the primal problem if either the primal or the dual problem has a finite optimum, then the other has a finite optimum, right? So that means that if the primal has a finite optimum, the dual also has. If the dual has, the finite also what has. Then it says if either problem has an unbounded solution, then the other has no feasible solution. Then the simplex procedure will give us the optimum solution if it exists for both the primal and its dual problems simultaneously. So that means that if you solve the primal problem from the simplex table, right, you are going to get both the solution of the primal and the dual. The same way if you solve the dual too, you get the solution for the primal too. Okay, and we will show you how to do that very soon. So I made mention of shadow prices, right? That when we convert the primal problem to a dual problem in the objective function, the new objective function, the coefficients, the decision variables, the y1, y2, and the rest, they are what we call shadow prices. So what are shadow prices? The shadow price is equal to the change in optimal objective function value per unit increase of a corresponding right hand side coefficient, because you realize that when we formulate the dual from the primal, the coefficients of the decision variables now are the right hand side we had in the primal problem. Okay, so the shadow price is equal to change in optimal objective function value per unit increase of a corresponding right hand side coefficient. So for each constraint, the shadow price tells how much the objective function will change if we change the right hand side of the constraint within the allowable increase and decrease limits. So mostly when we perform the sensitivity analysis, we get to know the sensitive range. That's the range in which we can either decrease or increase the right hand side. Okay. So note, the shadow prices are the objective function coefficients for the slack or surplus variables at the optimum solution. So when you solve the primal problem, right, the shadow prices are going to be the objective function coefficient for the slack or surplus variables at the optimum solution. So the main focus of a dual problem is to find for each resource its best shadow price, also known as marginal price. So by now you get how the reason why we are doing this thing. Okay, so now let's talk about the relationship between the primal problem and the dual, right? So when you have a primal problem and you solve it, and you have the final simplex tableau, right? How you can also get the solution for the dual and vice versa. So let's consider a problem here. We have maximize z equals 45x1 plus 80x2 subject to these constraints. This is the primal. If we decide to write a dual for it, we are going to get this. And by now you should know how we had that. You can pause the video and try and convert it. I think we've even done that in the video already. Okay, so if we solve this problem here, the primal problem here, this is going to be the final simplex tableau. Okay, right. So at the end of it, you are going to get S1 to be 24, S2 to be 14, and the maximum of Z to be 2200. And if we solve the dual problem that we have here, this is also going to be the final simplex tableau we have, right? And that is going to give us y1. Okay, actually the software I used, instead of y, it gave me x, but we used y1 and y2 here, right? So that means wherever you find x1 is y1. Okay, so that one will give us y1 to be 1 and y2 to be 4. Okay, and you see the minimum of z is 2200. So you realize that the value that we had here is the same as the maximum value that we are having for the primal problem. So that means that the objective function value that you have in both the primal and the dual is always the same. Okay, so when you are given a simplex table for a primal problem and they ask you to find the objective function coefficient for the dual problem, is going to be the same thing as the one you had in the primal. Okay, just that if one is a maximum value, one will be a minimum value. Okay, all right, so you could see that our x1 and x2 were, so x1 was 24 and x2 was what, 14. So this is from the primal problem, right? So when we go to the dual problem, let's see how we are going to locate that. So we see that when it comes to the dual problem, the x1 value, right, is the value for s1 at cj minus zg, right? So we always take the absolute value of it. So s1 corresponds to the value for y1. So y1 is equal to what? It's 24. And y2 is equal to what? Um, actually, I think it's s1 because we are talking about the primary problem. So s1 is 24 and s2 is what? 14. So you can see that this is the what? Dual, the simplex for the dual. But we're able to get the solution of the primal from it. If you can see that. The same way when we come to, the solution for the dual is also y1 is 1 and y2 is 4, right? And with that one, so we can get it from the primal problem here. So we have it. It's always this rule, right? But you mostly find the absolute value of it. So here we have y1 to be absolute value of negative 1, which is 1, and y2 to be, which is 4. Okay, so the reason why some of them are negative and positive is because of maximization in one sense and minimization in the other sense. Okay, all right, so that means that when you have a primal problem and you're asked to find the marginal profit or the solution to the dual problem, it is, you come to the cj minus zg, right, rule, and you look for the values for the slack variables, okay, under this, right, and you find the magnitude of them, and those are the values that are going to correspond to your y1, y2, y3 to yn. Okay, so there's a relationship between the two. So when you have one table, the table for primal, you can get the solution for the dual. The same way, if you have the table for the dual, you can get the solution to the what, primal. Okay, so if I were you, to make sure you really understand this, the rest of the primal problems that we converted to the dual, you can use a software, right, to find a solution to both of them and compare the answers. you realize how clear the relationship is. Okay, so yeah, thank you very much, and I'm going to see you in the next video where we talk about sensitivity analysis. Okay, so see you.